class. We discussed about the electrical activity of the heart, and we learned that heart conductive tissue consists of 5 different structures, including sinoatrial node or SA node, internodal pathway, AV node, bundle of His, and right and left bundle branches, and finally the Purkinje fibers that penetrate the myocardium, ventricular myocardial cells, and transmitted the action potentials with high velocity throughout both ventricles. In this manner, we have a spread of action potential in syncytium of atriomes and syncytiums of ventricles. Today we want to discuss about the ECG and the different waves in ECG. Please pay attention to this slide. At A, you can see a part of myocardial cells, a thickness of the wall of the heart, a piece of muscle, and excitable tissue. And you see that in left parts, we have depolarizations, and the inside of the cells is positive relative to the outside of the cells, which is negative. You learn that we have resting membrane potentials, we have resting membrane potential about minus 90 millivolts at rest, and during the action potentials we have the polarizations, and we have rapid movement of the positive charge inward the cells. So, and the rest of these cells is in resting state, and inside the cells is negative and related to the outside of the cell membrane, which is positive. So if we put a voltmeter electrodes on outside of these excitable cells or fibers or piece of myocardium, we have 2 points. At this point, this electrode see negative charges, and at this point this electrode sees the positive charges, and the difference between these 2 points is recorded by the electrovoltmeter according to this shape to these amounts of voltage toward the positive electrodes. It means that the potentials that this electrode, the right electrode, is recorded is more than the left side. And we can show this by the upward deflection of this line or curve, which show us in vertical axis the voltage changes from baseline toward positive charge or negative charge. So the polarizations by definition is shown as an upward curve. In B, the polarization waves spread throughout cells and all points are depolarized. So we reach to the maximum level of the polarizations, and then the electrovoltmeter recorded nothing or returned to the zero positions because there is no differences between this point and this point, and both of them are seeing negative charges, and there is no differences between these two electrodes, so we recorded anything, and we are in the baseline here. In C, again, these cells start to repolarization. After depolarization and remaining depolarized, they start to repolarization. During the repolarization phase, as you see, the first part of the depolarizations is returned to its original states, and the inside of the cell become negative related to the outward of the cell, which is positive. So again, we have two conditions. Right electrode, C regions which are in depolarized states and are looking negative charges outside the cells, and left electrode is looking toward the positive charges and region of the cell which is in resting state or polarized states, and inside the cell are negative. So again, between these two electrodes we have differences which their recorder show it as a negative voltage, because now the positive electrodes in the right side is attached to positive pole of device, and the negative electrode is seeing positive charges, so the voltage is by negative electrode is more than positive electrodes. So we have downward deflection to show differences between this position with this one. In both of them we have an electrical gradients or differences between two electrodes, but in A the direction is from positive or left side toward right side, from positive to negatives, and outside the cells from negatives toward positives, from left to right. But in C, outside the cell we have this direction from negative to positive, and this direction is reversed to the first one in A. So if we show upward deflection for depolarizing waves in A, we show downward deflection for these currents, which is recorded between these two electrodes. And finally, after repolarization of all muscle fibers, there is no differences between outside and between two electrodes, because both of them are looking to positive charges. So we record nothing, and again we have an isoelectric line. So in this shape we learn different points. First we learn that we have directions in current. Electrical current have directions from negative toward positive poles, from negative toward positive, from negative toward positive. 2. This by definition is shown as upward or downward or right deviations toward positive pole or left deviations toward negative poles. 3. We learned that if there was no differences or no electrical gradients between two electrodes, there is no currents, and we record isoelectric line, as you see here, isoelectric line, because there is no differences between negative charge and negative charge, or between these two electrodes in B, when all fibers are in depolarized states or in the plateau of the action potentials here, and also in D, when all cells in the resting states, in the resting membrane potentials, and outside of the cells have positive charges, so there is no gradient between these two electrodes. Again, we record isoelectric line, or there is no differences between these two electrodes. Now, if we look to the heart as a muscle mass that undergoing depolarizations, depolarized states, and repolarizations, and repeat these properties again and again, we have different phases: depolarizations, plateau of action potential, and repolarizations. During depolarizations, if we put some electrodes on the chest wall, we can see an electrical differences between these between 2 points, because the depolarization is spread throughout the heart, and we can record. And during plateau, when all cardiac muscle, multicular muscles are in depolarized states, we record nothing. Or during the plateau of the action potentials, we have this striate line or isoelectric lines. And when the cells start to repolarize, again between two electrodes on the chest wall, we have a current, and this current will record the T waves. And this pattern repeated again and again: QRS complex, P waves, QRS complex, P waves, due to depolarizations and repolarizations. Due to depolarizations and repolarization. Please note that during the plateau of the action potential, while all cells are in depolarized states, there is no gradient between two electrodes on the surface of the chest wall, and there is no record, and we have an striate line or isoelectric line during plateau of the action potentials. And also during the resting states in diastole, when all cells are in resting states, again we record nothing, and we have in isoelectric lines. So the isoelectric lines only show us two electrodes is 0, and it is not show us the absolute value of potentials. So that the absolute value of potentials may be very different. As you see here in B, the absolute value of potentials between outside of the cells is negative at the level of minus 19 millivolts during depolarization states of the cells. And during the resting states, the outside of the cells is near the 0 potentials, and the inside of the cells is at the level of 19 millivolts, minus 19 millivolts. So the absolute values are not shown in these experiments, and only the differences between two electrodes will be recorded. And in B and C, when all two electrodes see the same charges, or either positive, and there is no electrical gradient, or delta E electrical gradient is 0, we have isoelectric line. But the absolute value of this isoelectric line and this one is very, very different. Again, in the ECG, you must know that this isoelectric line, which is representation of plateau of the action potentials, have absolute positive charges, but this isoelectric line, which represents the diastolic part of the heart cycle, and all cells are in repolarized states, show us an absolute value near to 0. Look at this slide. At this slide, we put two electrodes on the external surface or outside of the cells or a piece of different myofibrils of the cardiomyocyte, or simply we put two electrodes on the external surface of the heart or on the chest wall and record the differences between two electrodes. In this situation, the negative part of the device or voltmeter are located here, and the positive electrodes of the device, which is connected to the positive pole, are placed here, and both of them are seeing positive charges or region of the cells that are not stimulated and are in resting states. In resting state, you know that the inner of the cell is negative and the outside of the cells has positive charges. So we have, at this situation, we put two electrodes on the outside of the myocardial cells or heart, outside of the cells, and both electrodes see positive charge, so there is no electrical gradient between these two electrodes, and we record nothing or zero potentials, as you see here. In these situations, the negative electrodes seeing negative charge and the positive electrodes are put on the positive charge. It means that some parts of the cells or cardiomyocytes are depolarized and the inside of the cells convert to positive and the outside of the cells is negative, and the remaining are still in resting states and outside of the cells are positives and inside of the cells are negative. So we put two electrodes on external surface at parts that are depolarized and is shown in red color in this shape, and on external surface of the heart at positions that are not still depolarized and are in resting states and outside of the cells have positive charges. So between these two electrodes we have electrical gradients, and because the positive electrodes seeing positive charge and negative electrodes seeing negative charge, so the deviations is toward the positive electrodes, and it means that the positive electrodes see more voltage, positive voltage, than the other electrodes. And in last situations, in the left side, we have a reverse order. The positive electrodes are put on the active or depolarized myocardium, and the negative electrodes is placed on the resting myocardium with positive charges at our outer surface. So now the positive electrodes see negative charges and the negative electrodes see the positive charges, and there is electrical gradient between these two electrodes, but now we have leftward deviations of the voltmeter, and show us the negative electrodes see more potentials or positive charge than the positive electrodes of the voltmeter. So what we recorded from the heart and any other excitable cells as an extracellular recording, which means putting the electrode outside of the cells, is depending on the place of the electrodes and the relative charges that are seeing by two electrodes. This type of recording is called bipolar 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 recording. Extracellular bipolar recording, and we use extracellular bipolar recording for ECG recording and also extracellular recording. Look at this slide. Show us we put two electrodes on the external surface of the chest wall and show us the heart start a new cycle, and the depolarization wave depolarize the septum, interventricular septums, and continue to travel to the apex of the heart and invade the thickness of the right and left ventricular walls. The movement of the polarization wave in the heart muscle provided an electrical field around the heart, which, due to electrolysis in our bodies and extracellular fluids, conducted to the surface of the body, and we can record these potentials by an electrovoltmeter, as you see here. Again, we have two electrodes which are connected to the positive and negative end of the device, and we are placed them on A point and B point. As you see here, the spread of the electrical fields from the heart toward the surface is from the upward and right toward the left side, but because the heart have this position in our chest walls, and the atrium and sinoatrial node, which the SA node, this mouse is have technical errors. بله سلام، کلاس هستم، میشه بعداً صحبت کنید؟ مرسی، خواهش میکنم، ببخشید، خواهش میکنم. As you know, we have SA node in right atrium of the heart, and from the SA node the electrical impulse travels toward the AV node, and from the AV node toward the His bundle, and then to the right and left ventricle. So the electrical impulse from the heart in the heart starts from the SA node which is located in the right atrium. So it starts from the right side and travels toward the apex of the heart, which is located at the left side. So we have this direction from right and above toward the left and bottom. During this spread, the electrical impulse of the heart causes electrical fields around the heart muscle. And so the first part of the heart, which is depolarized, and the last one, which is still in resting state, have this positive charge and this negative charge inside the cells. And we have this direction for spread of the polarization wave, as you see here in this shape. But it is inside the cells, and outside the cells, the same cells, we have this negative charge at the outside and this positive charge at the outside of these cells. So we have this direction of spread of the polarization from negative toward positive charges. We have this direction from negative toward positives. So because we put the B electrodes, which is connected to the positive charge, to the left side, and A electrode, which is located to the negative charges at the right side, so we have these deviations that show us we have an electrical gradient between these two electrodes from right, and with this direction from right and above toward the left and bottom. We can put different electrodes on different positions in the bipolar recording of the electrical activity of the heart. We can place the electrode in 3 different situations. First one, which is called lead 1. In lead 1, we connect the positive electrode to left hand and negative electrode to right hand. So, or we can put these electrodes on the arm, the negative electrode on the right arm and the positive electrode on the left arm. So we have these directions from negative to the positive, which is called lead 1. In this situation, the differences between these 2 points would be equal to the differences between these 2 numbers, minus 0.2, positive 0.3, and the difference between them is equal to the 0.5 toward the positive electrodes. In lead 2, again, we can connect the positive electrodes to left leg, and negative electrode still is connected to the right hand. So we have these situations: negative electrode connected to the right arm, and the positive electrodes is connected to the left leg. We have this one. Again, we can see that the potential at this point is equal to the 1 plus 1 millivolts, and the potential at this point is the same, minus 0.2 millivolts, and the device or voltmeter show us the differences between these 2 electrodes, which have equal to this value, positive 1.2 millivolts. In the last situation, which is called lead 3, we connect negative electrodes to right hand and positive electrode to left leg, to left hand and left leg. So the left arm is connected to negative electrode and the left leg to positive electrode, and we have this one. Again, you can see that in lead 3 we record the differences between positive and negative electrodes, the difference between 1 millivolts and 0.3 millivolts in lead 3, which is equal to 0.7 millivolts. So the amount of the voltage between two electrodes in extracellular bipolar recording is dependent on the location of the electrodes relative to each other and relative to the positive and negative poles of the voltmeters. Indeed, in the chest wall, anterior chest wall, we can consider a triangle with three directions, which is called lead 1, lead 2, and lead 3. And according to the law of the mathematics, we can put the end of one vectors to the start of the another vectors, and we can connect the initial points of the first vector to the end points of the next vector in this manner, and we can calculate the sum of two vectors. As you note here, we can write this equation: 1 and 3 would be equal to 2. As you see here, this value plus this value would be equal to this one. In another word, the amount of the voltage which is recorded in lead 1 and the amount of the voltage which is recorded in lead 3, the sum of these two voltages would be equal to the voltages that is recorded in lead 2. Indeed, lead 2 is the sum of lead 1 and lead 3. It is the law of Einthoven. And the triangles in the anterior surface of the chest wall, which show us the relative order of different leads, lead 1, lead 3, and lead 2, provide the Einthoven triangles. So, the meaning of lead means the position of recording electrode on the surface of our body. In ECG or recording of electrical activity of the heart from the surface of the body, we have 12 leads. Three of them are bipolar leads, as you see in this shape. We have two electrodes, and we record the difference between the differences in the voltage between two electrodes with different locations: lead 1, lead 2, and lead 3. And between these three leads we have Einthoven relationships. So we have 3 bipolar leads, and we have 9 unipolar leads, and collectively in normal ECG we have 12 leads. The meaning of unipolar leads: unipolar leads means that we have one recording electrodes which records the potentials, positive or negatives, relative to the reference or zero potentials. So we don't have two electrodes, we have only one recording electrodes. So this is called unipolar leads. In normal ECG, we have three bipolar leads, lead 1, lead 2, and lead 3, and we have 9 unipolar leads. These 9 unipolar leads will be categorized in two categories. Limb leads, unipolar limb leads, AVR, AVL, and AVF. So we have three unipolar limb leads and six precordial or tierce unipolar leads. Here we see lead 1, lead 2, and lead 3 ECG from a normal heart. We have upward or positive waves in lead 1. We have some negative waves as you see here. This wave, downward deflection in lead 2, or this one, these waves, downward or negative waves, and upward or positive waves. Indeed, we have one thing which can be seen from different viewpoints. So we have different type of ECG waves in different leads, lead 1, lead 2, and lead 3. All of them show us the activity of one heart in time, but because they're located in different places, the electrodes record different voltages. So the shape and the amplitude of the waves are not identical to each other, and there is some differences between lead 1, lead 2, and lead 3. But all of them have a similar patterns, have QRS complex, have T waves, have P waves, and the relationship or the distances between these waves are regular and similar. In this shape, you can see the 9 unipolar position of different electrodes in normal ECG recording. AVR, AVL, and AVM unipolar limb leads means that these electrodes record the potential at these points that is originate from the heart relative to the zero potentials of the ground. These electrodes or records the potential at these points from the origin of the heart relative to the zero potentials of the ground. And this one records the potential at these points relative to the zero potentials of the ground or earth, or reference, as a reference, zero reference. So we have only one recording electrode. So these electrodes are called unipolar limb leads because they are attached to the limbs. And we also have 6 precordial or chest leads which records unipolar recording extracellular unipolar external surface of the heart, and they are located in the anterior of the chest wall. You must know the precise location of these leads. Lead 1 is located at the right side of the sternum at the fourth intercostal space. Lead 2 precordial lead 2 is located on the left side of the sternal bone at the fourth intercostal space. Lead 4 is located between at the crossing point of the mid-clavicular line, the clavicular bone, mid-clavicular line with the fifth intercostal space. This is the location of lead 4. Lead 5 and lead 6 are on the fifth intercostal space at the anterior axillary line, crossing point at the anterior axillary line and mid axillary line at this point. And finally, lead 3 is located between lead 2 and lead 4. So you learn the location of 12 leads of ECG. 12 leads of ECG can be categorized in two waves. 3 of them are bipolar, lead 1, 2, and 3. 9 are unipolars, and these 9 unipolar leads can be categorized to 3 unipolar limb leads and 6 unipolar precordial leads. Show you the recording of chest leads or precordial leads, which are unipolar leads, from V1 to V6, from the right side toward the left side, as you see here. Lead 1, V1, is located on the right side, and V6 is located extremely at the left side. So, in precordial chest wall, in the anterior chest wall or chest leads, we have V1 to V6 in order from the right to the left. And you know also that lead 1 is located on right atrium and the origin of the cardiac impulse, because SA node is located in the right atrium. At this point, the impulse starts and spreads throughout the heart in this direction, from right and above toward the apex and the bottom left side. So from the above and right toward the bottom and left side at these directions. So when we recorded the electrical activity of the heart in unipolar chest leads, we can see these patterns. From right side toward the left side, we have very little waves, positive waves, that step by step grows and undergoing high amplitudes, and in reverse we have deep negative waves which will be disappear when we move toward the left side. It is because that when the polarization waves move toward recording electrodes, it causes upward deflections, and when the polarization waves move away from a positive recording electrode, it is recorded as negative deflections. We discuss about this pattern here. Look at this picture. At A, we have a depolarization wave in these directions, from negative to positive at the outside of the cells, from negative to positive at the outside of the cells. Or the polarization wave moves toward positive electrodes, toward these electrodes. So we have an upward waves. But in C, the direction of electrical current is from negative toward the positive. So we have a current which is in a reverse directions from negative toward positive charge during repolarization phase. During repolarization phase, when the cells is undergoing repolarizations, so we have again electrical gradient in a reverse mode. So we record downward deflections. So, as a general rule, when the depolarization wave moves toward positive electrodes, it causes upward deflection of the voltmeter. And when the depolarization wave goes away from the positive electrodes, it causes a negative curve or deflections. You can see this at this shape. In precordial chest leads, the depolarization waves moves from right side to the left side. So each time it causes more positive or upward waves. In this direction. And finally, you can see the shape of ECG waves in unipolar limb leads in leads AVR, AVL, and AVF, which we put the recording electrode on left leg, AVF, on right arm, AVR, and on left arm, AVL. Again, you can see that the shape of the recording waves is different because it is dependent on the locations of the recording electrode relative to the depolarization waves which travels toward recording electrode or away from the electrodes. ECG is a time voltage signal. Time voltage. Indeed, in ECG we have two entities. We have time, T, in horizontal line, and we have changes in the voltage in vertical axis. Indeed, as the action potentials, which we show as depolarization and repolarizations, the action potentials is a simple action potential or a spike action potentials or a plateau action potentials like cardiac muscles have a depolarization phase and a repolarization phase. We have voltage during time. In horizontal line, we have time, and in vertical line, we have change depolarizations and repolarizations. And we record these changes as ECG. So in the ECG, we have two parameters, time in horizontal line and changes in the voltage in the vertical line or axis. We have different waves. We have P waves, the first upward curve or wave. We have Q wave, which is a negative wave. We have R wave, which is the positive wave after the Q. And again, we have a negative wave, which is called S wave. And finally, we have a positive wave, which is called T wave. So, we have Q, R, S, and T. Because the Q, R, and S waves start and are connected to each other immediately after each other, they collectively called QRS complex, QRS complex. So in the ECG, we have P, QRS, and T wave. P, QRS complex, and T. P, QRS complex, and T. P is due to the polarization of both atrium. Q, R, and S are due to the depolarization phase of ventricles, and T is due to the repolarization of ventricles. Please note that there is no record from repolarization phase of atrium in normal ECG because it is masked or hidden by changes in the complex. In ECG, we have also different intervals or times. For example, the distance between two adjacent R waves, which is called RR interval, or the distance between the start of P wave and the start of the QRS complex, PR interval, or ST segment, the distance between the end of S wave and the start of T wave, which is called ST segment. QRS durations, which is the time between the start of the Q wave until the end of the S wave, or QT interval between the start of the QRS complex and the end of T waves. All of these times have important informations and are useful in clinical practice, and you must learn the normal values of them. For example, the normal value for PR is 0.2 seconds. More than this value, first degree heart block. Or the normal value of QRS durations is 2 to 3 maximum small square, as you see here. Each small square is equal to 0.04 seconds, and 5 small square is equal to 5 this value, which would be equal to 0.2 millivolts, as you see here. 1 second after 5 small square change 0.2 seconds. Again, it is equal to 1.4 small squares at 0.04 seconds. In vertical axis, each 10 squares is equal to 1 millivolts voltage, and this can be upward or downward or negative charge. The upward or downward deflections is determined by the position of the electron, movement of the polarization wave toward the electrodes or away from the recording electrodes. And also please note that the SA node activity and AV node activity, the spread of impulse in the bundle and bundle branches cannot be detected in normal ECG, and the P waves is the sum of all electrical activities in both atrium, including the conductive tissue of the heart, SA node, and but we know that these activities occur in orders and step by step after each other, But due to the long duration of the plateau action potential of the heart muscles, we record them as a P wave. If we return to the first slide, we learned that if we put negative electrodes on right arm and positive electrodes on left arm, indeed we have lead 1. We record the potentials of the heart between these 2 points, from negative toward the positive. And in the same manner, we can record in lead 2 and lead 3, 3 bipolar limb leads, and also when we attach the recording electrode to the left arm and record the different potentials relative to the zero or reference potentials of the Earth, it is called unipolar limb leads, AVL, AVR, and AVF. AVL, AVR, and AVF. Unipolar limb leads. So we have 6 limb leads. 3 of them are bipolar, and 3 of them are unipolars. For each lead, we can consider it an degree. For example, lead 1 from right arm to the left arm at these directions. Indeed, it is like x-axis or horizontal line, which is equal to 0 angulation with the horizontal line. So we can consider it 0 degree for lead 1. In lead 2, we have these directions from right arm to the left leg. So from lead 2, we have these directions, which would be equal to this degree from horizontal line, or we can consider it 60 degree for lead 2. For lead 3, the degree with horizontal line would be equal to this one, or 120, but we can move the lead 3 parallels to and put it here like this. From here, this place, and place lead 3 at these positions. Because we have a parallel shift in the mathematics, we can have parallel shifts in vectors. So in lead degree. For AVL, we can consider it negative 30 degrees, and for AVF, the degree is vertical, and for AVR we have. So for each leads we have an degree, and accordingly we can determine the heart axis, electrical axis of the heart, and its degree. For example, in this heart, the electrical axis is in normal situations and in normal range, and its normal range is 60 degrees. But some hearts are more horizontal and some hearts are more vertical. It is dependent on the size and position of the person, and also on the thickness of the left and right ventricular wall. The normal range of cardiac electrical axis is from 0 to 100 degree, and the exact value is 59 degree. So you must know the direction of different leads and their degrees. For example, you must know that these vectors show us AVF with 90 degrees relative to the horizontal line. We can use the ECG waves to determine the heart electrical axis. The heart electrical axis can be determined by simple mathematical law. You know that if we draw a x and y axis, we can represent different vectors on these two axes. In a simple way, you can see a pen or any other cylindrical shapes from above, which will provide you this shape. Also, you can see them at this base, which will be provide for you this shape. So it is also the rule for vectors. This vector A, in lead 1 will be seen as the B vector. Indeed, we put the initial points of vector A on the 0 or reference points, and the end, and from the end points we can draw a vertical line to that axis or lead 1. So we have B. The B vector is the representation of A vectors in lead 1. If I can, pardon me, this mouse is not work correctly and will consider that we have this axis X and Y. We looking to this vector A. When we looking to the A from the x-axis, we can see this one. We have the equal vectors at the same directions. But when we look at this vector from Y, we can only see a point. When we draw a vectors, indeed we do this. We from the start and the end we have two vertical lines, and then we connect these 2 points to each other. So we can represent these vectors on its x-axis and 1 as 1, and in the y-axis from the start points and the end points we draw the vertical lines, and we have these vectors 2. So the representations of one vectors in two axes will provide two vectors with different lengths or size. When a vector is parallel to the axis, it would be provide the maximum values, and when it is perpendicular to an axis, it will be presented as a point only, because both points will be put at the same place. Suggest that we want to see this vector A on in x-axis. From the start points here, we draw a vertical line. From the end point here, we draw a vertical line, and both of them will be on each other. And from the on the x-axis, the representation of A vectors is only a point. But in the y-axis, this vector will be represented as equal vectors. So we have the electrical axis of the heart as A, and we want to draw its shape in lead 1. So we put the initial points on the center of the vectors and draw the vectors at the same directions and same angle degree from relative to the horizontal lines, and we draw the perpendicular line from the endpoints to that axis or lead 1, and we have B as the representations of A vectors on lead 1. Here again we have an electrical axis which is due to the spread of electrical activity in the interventricular septums from the left side toward the apex and relatively to the right side. The shape of these vectors, which is very relative to the initial or vectors, and also in the reverse directions from positive toward the negative. So it will be recorded as a negative waves, not as a positive or upward deflections. We have one heart which start depolarization in SA node, and this depolarization is spread throughout different parts of the heart. The main electrical axis of the heart is this vector from the right side and above toward the left side and bottom, with this degree or nearly 60 degree relative to the horizontal line, this degree. It is shown as A vector in this shape. The A vector is the electrical axis of a normal heart, which show us the spread of action potentials in the heart from SA node toward the apex of the heart. Then we put the electrodes of the ECG device on the surface of the chest wall, lead 1, lead 2, and lead 3. And we record these potentials which originates from the heart. In lead 1, we record the image of this electrical axis of the heart as this wave, as B. In lead 2, we record the electrical axis of the heart A as C. Because the electrical axis of the heart in normal situations is very close to the degree of the lead 2, you can see that the value of C vectors is near to A and is much higher than B, because the axis of the lead 1 is 0, but the axis of lead 2 is 60. So the image of electrical axis of the heart A in lead 1 is B and is little than A, and in 2 is C, which is more equal to A. And finally, in lead 3, as you see here, lead 3, which was here, left arm negative and left leg positive electrodes, which we move it and put it here with this degree. You can see that the representation of electrical axis of the heart, which start from the drawing the perpendicular line to lead 3, will provide the vector D. So the vector D is less than B and C, but still is a positive or upward waves, because the positive end is looking to the positive end of the lead 3. In C, the positive end is looking toward the positive ends of lead 2, and in B, the positive ends looking toward the positive end of the same leads. So we are looking to these electrodes, lead 1, lead 2, and lead 3. And for each wave, for example, for T waves, or for QRS complex, or for P waves, or any other waves in the ECG, we can calculate the axis of the heart according to these calculations. For example, for QRS complex, you can see that in lead 1 we have this complex. The amplitude of this complex is equal to positive 5, because we have positive 5 small square from the baseline up to the peak of the R waves. But in lead 2, you can see that we have 5, 5, and 2. So we have 12 voltages in lead 2. And lead 3, in lead 3, we have 5 and 2, or positive 7 millivolts. So for this heart, the electrical axis of the heart would be this one. We draw lead 1, we draw lead 2, and we draw lead 3. In lead 1, we have recorded 5 positive charges. So toward the positive end of lead 1, we draw 5 units. We have this one. And in lead 2, we have positive 12 recording of QRS complex. So in lead 2, toward the positive end, we draw the positive 12s, this one. And when we draw the perpendicular lines to lead 1 and lead 2, they cross each other at this point. If we connect this point to the origin of the axis, we have this electrical line. Indeed, this heart have this electrical axis, which is represented in lead 1 as these vectors, or this amount of changes in the voltage or QRS complex, and it's represented in lead 2 at these 12 positive changes in voltage, and these vectors in lead 3 would be represented at these values, positive 7 upward. So these simple rules, we can calculate the electrical axis of the heart with only using 2 of 3 bipolar limb leads. By 1 and 2, or by 2 and 3, or by 1 and 3, we can calculate the heart axis. And also we know that there is this relationship, 1 pulse 3 would be equal to Einthoven rules. In this slide, you can see the step-by-step or moments-by-moments spread of the polarization wave throughout the heart in both ventricles. The first part of the ventricles that receive the depolarization waves is the left side of the interventricular septums. Then the septums start and continue the depolarizations toward the apex, and from the left side toward the right side. Then the depolarization waves starts to invade to the thickness of the right and left ventricular walls, and transmural spread occurs, and it returns toward the last part of the base of the left ventricles. And finally, all syncytium of both ventricles undergoing depolarizations. When we draw the electrical axis of the heart in lead 1, lead 2, and lead 3, we can see these shapes. Growth of the polarization waves until the peak, and again decrease in the polarizations because the differences between two electrodes diminishes. And finally, after the polarization of all parts of the ventricles, there is no differences between the two electrodes, and the electrical gradients between two electrodes is 0, and we record nothing. So again, in lead 1, lead 2, and lead 3, at the end we return to the isoelectric line. So we first start from the isoelectric line to depolarize, reaching to the maximum value, and then decreasing the voltage until it again reach to the isoelectric line again, and will provided us the R waves or QRS complex. For repolarizations, we can also draw the same in the same manner, T wave. The repolarizations also spread from the apex toward the base of the heart. So, indeed, it is like that the depolarization wave which moves from the upward and right side toward the left side and bottom now move backs in a reverse directions moves backs, and all parts of the heart again undergoing repolarizations, and each step the voltage decrease and decrease, so until from full depolarization states is changed to full repolarization states. Again, we start from the isoelectric line. We have upward deflections for the repolarizations of the both ventricles, and after complete of repolarization of both ventricles, we again are in the isoelectric line. Please note that according to this shape, depolarizations upward, repolarizations downward. So we must have R wave and R waves and T waves, or P waves and P waves. Depolarization of the atrium and repolarizations of atriums. Upward depolarization of ventricles and downward repolarization of ventricles. But there is a differences. In atriums, we have the upward depolarization wave and downward repolarization waves, but the time of repolarization of atriums is at the same time of depolarization of ventricles, and because the mass of ventricular muscles is more than the atriums, so we have much more voltages due to depolarization of ventricles, and these large depolarizations cancel out the negative depolarizations of the negative repolarizations of the atriums. So the net would be a positive upward movement of the voltage. So in the normal ECG, we don't see repolarizations wave of atrial muscles because it is masked by the depolarization waves of ventricles. It is similar to the net of diffusion. We learned that we have diffusion from high concentrations toward the low concentrations, but at the same time we have movement of molecules from low concentrations toward the high concentrations, but the net effects would be the difference between these two movements, and we have a net diffusion from high concentrations toward the low concentrations points. In ECG, we have depolarizations of atriums, and after a time we have repolarization of atriums, but we don't see this repolarization in ECG because at the same time we have depolarization of ventricles, high voltages, upward voltages of the depolarizations, and these high voltages, for example, positive 20 millivolts for depolarization of ventricles and minus 5 millivolts for repolarization of atrioms. So the only thing is a positive 15 millivolts, which is the net effect of these two opposing curves. It is for atrioms. In the ventricles, the direction of depolarizations and direction of repolarizations is the same, and the vectors from negative toward the positive charge during depolarization and from negative to positive charge during repolarizations. And both vectors have the same directions during depolarization electrodes and during repolarizations from the last point, which is undergoing depolarizations, is the first one which undergoing repolarizations. So the direction of repolarizations is also the same, and indeed the depolarizations wave only works as a backward without any changes in its directions. So for ventricles, the depolarization wave and repolarization waves have same direction, and both of them are upwards. So for atrial muscles, we have depolarization waves of atrioms as P waves and repolarization of atrial muscles at repolarization waves, negative waves. But in normal ECG, this negative wave is masked by QRS complex, which occur at the same times. We have the mean electrical axis of the heart at these directions, but this mean electrical axis of the heart have changes in each cycle, cardiac cycles, in different moments. At first, it moves from left side of the interventricular septum toward the right side, so we have these directions, then spread throughout the normal directions, and at the end it turns toward the base of the left ventricles, so at this direction. So at the beginning of the QRS complex, we have a wave from left toward the right. It is in opposite to the normal mean electrical axis of the heart. So we record negative waves as Q waves. Then we have R waves due to a spread of the electrical axis toward the apex. And at the end, we also have another negative waves as S waves because of the changes in the direction of the electrical axis from the bottom toward the apex, base of the heart, from the apex toward the base of the heart in reverse mode. So by we look to the ECG and we measure the voltages, QRS complex voltages, we as positive and negative, we sum the positive and negative changes in the voltage in QRS complex. For example, minus 1, minus 3, and positive 8 would be equal to positive 4. The sum of these changes in the QRS complexes is represented on the same leads. For example, in lead 1, so in lead 1 we draw a vectors positive, so toward the positive ends, and with this value 4. So we have these vectors. In lead 3, for examples, again we have a positive, so we have toward the positive ends and with the amount of the QRS complex sum of positive and negative charges, and then at the end points we draw a perpendicular line to that axis 3, lead 3, and to from this lead 1 to lead 1, and at the point which these two perpendicular lines cross each other, we connect this point to the origins or the reference points, and this would be the electrical axis of this heart, which is represented as these vectors in lead 1 and as these vectors in lead 3. Electrical axis of the heart can be changed in different situations. For example, as you see here in this ECG, you can see that in lead 1 we have a prominent positive QRS complex, and in lead 3 we have a prominent negative QRS complex. So in lead 3 we draw toward the negative charge. For example, the amount of QRS complex would be here. In lead 1 would be here toward the positive charge because the sum is upward or positives, so toward the positive charge. Perpendicular lines, cross points of perpendicular lines connecting to the origin. So the electrical axis of this heart is this, and it is deviated from the normal positions at here or this degree. It is deviated toward the left side. So we have left axis deviations. Left axis deviation of the electrical axis of the heart may be due to bundle branch block or may be due to hypertrophy of the left ventricular valve, for example, secondary to hypertensions and different situations. In this ECG, you can see a prominent negative QRS complex in lead 1. So in lead 1, the amount of this voltage is drawn toward the negative charge. But for example, in lead 3, we have a prominent positive QRS complex. So toward the positive ends, we have these vectors perpendicular to the end of two vectors and cross points and connecting to the origin. This is the electrical axis of this heart, which in lead 1 provided this or recorded as this QRS complex, and in lead 3 as this shape, and in lead 2 at this positive negative. Indeed, if we draw the axis of lead 2 here and we draw the electrical axis on lead 2, as you see here by a perpendicular line, you can see that the electrical axis in lead 2 has these values and toward the negative charge, which means that in lead 2 we have expected to have a negative QRS complex. And again, this axis is very deviated from the normal heart axis, which would be here, and we have right axis deviation. Right axis deviations may be due to hypertrophy of right ventricles or due to right bundle branch blocks and etc. This extremely left axis deviations is due to the bundle branch blocks, and the QRS duration is wide, and we have left axis deviations. You can see that in lead 1 we have positive QRS complex, and in lead 2 and 3 we have negative QRS complexes. Indeed, we have large Q waves in lead 3, and the sum of QRS complex is negatives because it's downward, and we put them toward the negative end of lead 3. But in lead 1 we put on the toward the positive end of the lead 1, and perpendicular of these two electrode with corresponding these points, which will provide this electrical axis for this heart, which have left axis deviations due to bundle branch block. Or in this shape, it is an abnormal ECG because the QRS complex in lead 1 is negative, as you see here, and in 2 and 3 we have positive QRS complexes, and we use lead 3, and by perpendicular line we have this crossing point, and indeed this is the electrical axis of this heart, which is in normal range, but we have wide QRS complex due to bundle branch block. Q waves is very important in ECG because a prominent Q waves or a Q wave with high durations or high voltage, or a Q wave that is large relative to the R waves, is a pathological waves that indicated a myocardial infarction. And Q waves, pathological Q waves in ECG remains permanently and alert us about a previous myocardial infarctions or necrosis of and death of some parts of myocardium. We also have current of injury in ECG. The current of injury of the ECG is due to an injured area in the myocardium that provided a local current between damaged cells and normal cells, and this electrical signals exist in resting states of the heart between normal and damaged tissue. But when the heart undergoing depolarization and all parts of the heart is depolarized, the current of injury is masked and there is no effects from current of injury in the ECG. But when the heart undergoing repolarization again from the injured area toward the normal tissue, we have an electrical gradient which is represented in the ECG as the current of injury, and the current of injury causes the shift between ST segment and TP segment. This shift is called the current of injury, and its amount is determined by the direction of the current of the injury. As you see here, for example, at this shape, we have this amount of the current of injury, these vectors, which in lead 1 and lead 2 and lead 3 have in different directions. Lead 1 toward negative ends, lead 3 toward positive ends, and lead 2 toward positive ends. So in lead 1, the isoelectric line started below the normal isoelectric line at here. In lead 2 and lead 3, it started from above the isoelectric lines at these positions. And when the heart undergoing depolarizations, at the end of the depolarizations, all the currents occur on the normal isoelectric lines because all parts of the heart is the same, have the same situations. But by a start of repolarization, again the current of injury show itself as deviation from isoelectric line. So we have this amount of current of injury or this amount of the current of injury, which disappeared after depolarization of all points of the myocardial cells. Indeed, we considered the junction between the S wave and isoelectric line as the G point, or the reference point of the isoelectric lines in ECG. G points, the point between the horizontal line and the end of S wave, is the reference points, because at this point, regarding the existence or absence of current of injury, all parts of the heart have the same situations, and all of them are depolarized, and there is disappearing of current of injury effects on ECG. But by repolarization phase, the current of injury again show itself as deviation from normal isoelectric line. So when we looking at this shape, we can see that we have in accordance as in normal ECG, we have P wave, QRS, and T waves, and again P wave, QRS, T waves, and the ST segment, which is represented the plateau of the action potentials, and the TP segment, which is the diastolic part of the heart and resting states. All of them are at the same line, and there is no differences between isoelectric line at ST segment and TP segment. But when there was a current of injury, there is a step and incontinuity between ST segment, as you see here, ST segment and TP segment, between ST segment and TP segment, and one of them is elevated or depressed related to the another one. It is called the current of injury. The amount of these deviations is called the current of injury, as you see here. The current of injury disappears by times and is due to the ischemia of the myocardial cells and damage. For example, after an acute damage, injury, ischemia and injury, we can see ST segment depression, but after a few weeks, this will be disappear and the pathological conditions recovers very good. But the Q waves is permanent and will remain in the ECG for long times. Different waves in ECG have diagnostic properties. For example, drug toxicity, for digital drug toxicity for in heart failure will provide the changes in T waves, biphasic T waves, and etc. ECG also is important for interpreting the rhythm of the heart, for the velocity of the heart. We can distinguishing the tachycardia or heartbeat more than 100 beats per minute, like this ECG, or bradycardia, or less, which means less than 60 beats per minute, like this ECG. We can distinguish different blocks: SA node, SA block, AV node block, first heart degree block, second heart degree block, and etc. Different premature beats: atrial premature beats, ventricular premature beats, paroxysmal tachycardia, ventricular fibrillation, ventricular flutters, atrial fibrillations, electrical alternance, and etc. And this pathological condition will be discussed in clinical courses, and the mechanism of re-entry and arrhythmogenicity in the heart and the mechanism of DC shock will be discussed in clinical practice and are not included in your course. So in summary, we learned that we have conductive tissue of the heart, which starts from the SA node travels between internal pathway to reach AV nodes. The conductive tissue between the atrium and the ventricular muscle is throughout the AV nodes. And the first part of the septum at the left side of the septum is depolarized. Then throughout the right and left bundle branch is spread throughout the interventricular septums and throughout the ventricular valves. And we have two types of action potentials in conductive tissue. In nodal pathway, SA node and AV node, we have a slow response. The mechanically active cardiomyocytes in the atriums and ventricles, we have plateau action potential. Purkinje fiber, we have long duration action potentials with very high amplitude and high velocity for conductive impulse simultaneously in both ventricles. It is the summary of my today. Thank you very much for your attention. I will put the content of this class on the Navid systems. You can study from the offline contents from the Navid, and if there was any question, I will ask. You can calculate ECG by dividing the time between two RR intervals. Time between two R waves in ECG is 1 second. It means that each 1 second we have 1 bits. So in 1 minute we have 6 T bits